Hey y'all. So today I'm going to be talking you through the Investigating Forces in Equilibrium lab. So this is an exploration that is going to help introduce us to the idea of balancing forces. It's going to help remind us of some of the things with vectors and breaking things into components. And it's also going to introduce us a little bit to the idea of uncertainty and error, error bars, things like that. And so my hope is through this lab to kind of introduce you to all those things. And a lot of those things, the error and the uncertainty, are things that IB perceives as being important. You're going to see an exam question that will include those types of things. All right, so without further ado, let's go into it. Before I get started, let me just show you a couple of things. This is the basic setup. All right, we have spring scales on either side. The spring scales measure force in newtons. One of the things I noticed is that when I hung them there initially, that they weren't on zero. So one of the things I did to start off was I re-zeroed them and I made sure that they were showing zero. If you didn't do that, it's likely that it was off by as much as maybe zero 0.2 or 0.4 newtons. And so you want to make sure to account for that when you do your uncertainty and your error at the end, is that you might have a little bit of variability from the actual value. That would be what we would call a systematic error, because that's something that every single time it would give me a force that's a little bit too big. Or if it was reading a little bit too low, it would be giving you something that is a little too low every time. That's something that because of my system, there's a mistake. And that's something that most of the time we can resolve. We can fix those systematic errors a lot of the time so that they don't occur at all. All right. The second thing is I am going to be using this app. This is PhyPhox, 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 and it's really nice for getting angles. You probably have other apps and things that you can use, but I've set it to inclination, and what you'll notice right now is that it's almost straight up and down, so that's 90 degrees to the horizontal, and as I turn it to the right, it starts to give me smaller and smaller numbers. In fact, if I go all the way to horizontal, that would give me pretty close to 0 degrees. I can't hold it perfectly. But again, you'll notice that there is some variability in the numbers as I'm holding it, and maybe plus or minus a degree or 2 degrees, maybe even more depending on how accurate I think that I'm measuring it when I actually put it on there. These are things that we want to recognize, things that we're going to think about in terms of uncertainty. But you'll notice that this is essentially the 0, and as I go up this way, it's now giving me this angle right here with respect to the horizontal. And so I'm getting 16 degrees, I'm getting 20, 40, 50 degrees, bigger and bigger angles until I go vertical, which that would then be a 90-degree angle with the horizontal. All right, so that's what I'm going to be using here. There are different settings in the app, so you just have to be careful when you're looking at it. Always say, okay, well, what's this? Is this 0 or is this 90 or is it 180? You know, what is it telling me? And then as you rotate it this way or that way, the accelerometers in phones are so cool. They do so many cool things. Anyway, so without further ado, let's go ahead and jump into the exploration itself. There's a little bit of prior work that we're going to do with the vectors, and then we'll jump right into the lab. All right? So one of the first things it asks us to do is to show our work in the image above to determine the horizontal and vertical components of each of the tensions. All right, so what that wants us to do is, you'll notice that tension 1 is up at an angle here, right? That's theta 1. And so it just wants us to break that down into a horizontal component. So I'm going to label that as T1x, and then a vertical component right here, which I'll label T1y. And so those are the components I'm looking for. Now you'll notice that T1y is the opposite side. And so if I do opposite over hypotenuse, that would be sine. So I could say sine of theta, theta 1, is equal to the opposite, which would be T1y, divided by T1. And you'll notice that all I have to do is multiply both sides by T1, and I now have an equation for T1y. So T1y is equal to T1 times sine of theta 1. Now, the reason why that's value is because now I have a vertical component that is equal to the two things that I can measure, the tension 1 and the angle 1. Okay, I can do the same thing on the other side, right, with tension 2. Here's my horizontal, here's my vertical, so I'm doing the two verticals first. So this one would be T2y and T2x. So the y again will be opposite over hypotenuse, so it should kind of make sense that this one will end up being that T2y is equal to T2 sine theta 2. And you can kind of talk yourself through that process if you need to. All right. Now, I'm also going to do the horizontal here. Okay, so the horizontal is going to be T1x. That's the adjacent side to the angle. So here's my angle. That's the adjacent side. So that would be adjacent over hypotenuse. Now, I'm not going to use the opposite side because then I'm relating two unknowns. This is something I can measure, so I want to relate this to the thing that I can measure. So that'll be adjacent over hypotenuse, which will be cosine of theta 1, equals T1x, that's the adjacent side, over the hypotenuse, which was just that T1. And again, you'll notice I just multiply both sides by T1, and so I end up with T1x equals T1 cosine theta 1. And similarly, we could get the same thing over here. One thing that I do want you to notice is that on this side, this is to the left, and so that would end up being a negative T1 cosine theta 1, whereas on this side, the T2x is just going to be T2 cosine theta 2, and that's positive. Okay, now what we know from our situation that these two horizontal pieces should be balanced, right? The weight is not moving side to side, it's in equilibrium, so these two should be balanced. The two vertical forces are now balancing the force of gravity, which is pulling down. And so you have those two forces that have those vertical components. So that's going to be important later. But for now, we've got it so that we have our vertical components and we have our horizontal components. And we'll come back to that shortly. But for now, let's go gather some data. All right, so at this point, we're ready to start gathering data. For this experiment, I've asked you to get 5 data points. Kind of as a minimum, if you remember from MYP likes for you to have 5 data points and 5 trials of those data points. This is not an official DP or MYP experiment, so we're just going to make sure that we have enough data that we can work with it. For today, I'm just going to say let's just get 5 data points and we'll deal with the uncertainty as it comes. All right? So obviously what we're doing here is we're going to hang a mass from the 2 spring scales, okay? And then I'm going to, looking at the picture here, right? I've got angle 1 and tension 1 that are over on the left-hand side, and then I've got angle 2 and tension 2 that are over on the right-hand side. And so as I do this, this right here is going to be angle 1, and the tension in this string, the force that this guy's reading, that's reading how much tension, the force that there is in the string. And so that's what I'm going to put in for T1. All right, so I'm going to go ahead and flip over that. I put it more or less right here in the middle, and so we can go ahead and get those angles. So remember, this was 0. If I line it up as best I can with that, looks like I'm getting about 19.8 plus or minus about a degree. And so I'm going to put that down for angle 1 is 19.8 and when I degrees. And then when I look at the scale here, it looks like it's at about 10.2, and so I'm going to put 10.2 newtons for T1. I'm going to go to the other side and do exactly the same thing. Okay, so here I'll notice that this is giving me 180 that I'm rotating up this way. So I'm going to need to do 180 minus 156. So 180 minus 156 is going to be 24. Okay, and you know, on the previous one I said 19.8, but I'm actually just going to use 20 degrees because I'm not getting this correct to the 10th of a degree. Let's be honest. Okay, I'm going to try to put the degree, and then I'll say it's probably plus or minus about a degree, maybe two when I do my uncertainty. All right. When you look at your numbers, you can kind of see how much it's fluctuating. In my case, I feel like plus or minus a degree is probably a fairly okay number there. So now I'm going to look at tension 2 here, which that one also looks like it's at about 10.2. So I'm going to write 10.2 newtons. That one I am going to write down the tenths because I feel like that one is a little more stationary. It's a little more stable. So I'm going to go ahead and put 10.2. But I notice that if I take it off and I try it again, what am I getting? Now it's a little less than 10.2, right? This one is actually... Well, that one's still right about at 10.2. But I'm noticing that there's some uncertainty in my spring scales, and I feel like that's probably going to be about plus or minus a tenth of a newton, 0.1 newtons. If you see more variability than that, obviously you can deal with that. But from what I'm seeing right now is that my angle is going to be about plus or minus maybe 1 degree, maybe 2 degrees. It just kind of depends. And then my forces are going to be about plus or minus 0.1 newtons. And so this is my first data point right here. I got the 20 degrees on the left-hand side. I got the 24 on the right-hand side. They were both approximately 10.2 newtons. I'm thinking of my uncertainty here, which I've noted right now is about plus or minus a degree. And then my uncertainty in my newtons, which I think is probably pretty close to 0.1. But again, you may have something different. If you didn't zero these to begin with, you might have maybe a 0.3 or a 0.4 when you look at the uncertainty of the force here. Okay, so now I'm going to move it to a different location. I'm just going to move it over to the left just a little bit, just like that. And so now I'm going to redo it. I may pick it up and put it back down again just to make sure that the spring scales are resetting, that they're giving me the values that I want. Okay, so this one looks like I got about 25 degrees, and it is popping up and down about a degree. So 25 degrees, I'm okay with that. And then this one over here looks to be about 160. And remember, that's from the 180. So I'm going to go with 20 degrees on this side. Okay, and that side, that's my side 2, looks to be about 10.1. And then this side right here looks to be closer to about 10.4. Okay, so I got 10.4 newtons on that side. So now I've got 2 data points. I'm just going to go ahead and grab a couple more. So I'm going to move it over just a little bit right there. So this side now says 164. All right, so that's going to give me 16 degrees over on the right-hand side, angle 2. And then this angle is getting a little bit steeper. This one looks to be about 31 degrees. So I'll put 31 there. And then I'll read the forces on the left-hand side here. It looks to be about 11. It's almost right in the middle of the 10 and 12, so I'm going to put that at 11 newtons. And then this one right here is at about, looks like about 9.2. All right. And so let's gather 2 more data points. We're almost there. So I put a little knot in the string because I noticed that if I go too far over, then when I let go, it starts sliding back. And so I made a little knot here to help me out so that it stays there and doesn't keep sliding. And so from here, I've got angle 1, which is about 35 degrees, and it's, again, plus or minus about 1. And then on this side, I've got 167, 168. So I'm going to go with 168. So that'll be a 12-degree angle there. And then I need the force. So this side looks to be about 11.2. And then this side over here looks to be about 8.5. All right, so 11.2 and 8.5. And then I'm going to do one more. I'm going to go all the way over here. Okay, and again, I've got another knot there to help me out. And so I'm going to get the last two angles. So this angle right here is about 40, 41. So I'm going to go with 41 there. And then this angle right here is now at 171.7.8. So I'm going to go 172. So 172, that means I'm 8 degrees off of 180. And then the forces, this one still looks like it's around 11. Yeah, it looks like about 11 newtons to me. And then this side is much less than it was before. This is down to about 7.6 newtons. All right, so I got my data. Okay, so there's my data. It's looking pretty good. I have no idea if that looks good, but I do have some data points here. And so at this point, I'm ready to move on and start doing some of the calculations. So let's switch screens and see what we can do with filling this out and trying to create the graph and see what else we got. Okay? Now that we've got our data here, we're going to go ahead and do the calculations. We're going to construct a process data table. So you'll recognize these expressions right here from the work that we did at the beginning. This was the horizontal tension, the horizontal component of tension 1. I put a negative here just to kind of remind myself that that's a negative. That was going to the left. And then I've got the horizontal tension of the second one, which was the tension going to the right. And then I've got the vertical tensions, both of which are going upwards, so I've left those both positive. Remember, those are the two that are going upwards that are going to hopefully balance the force of gravity on our mass. All right? So from here, I'm going to show you case 1, and then I'll go ahead and pause the video. You don't have to sit and watch all of this. But for case 1, I'm just going to go tension 1, so that would be 10.2. And then I'm going to multiply by the cosine of theta 1, which was 20 degrees. And so there we go. We get 9.58. So hopefully negative 9.58. All right. And then for the tension 2, that's just going to be the 10.2 times the cosine of 24. Just like that. And we get 9.32. All right, and then for the vertical tensions, that's going to be T1 sine of theta 1, so that's going to be the 10.2 times sine of 20, and so we get 3.49 there. These are all in newtons. You can put the newtons there if you want. These are all forces, so they're all in terms of newtons. That was what we measured up here, remember? And then we've got T2 sine of theta 2, so that would be the 10.2 times sine of 24, which was the angle 2 there. And so here we get 4.15 newtons. All right. So what we see is that these two are fairly close together, which is kind of what we hoped, right? We wanted the left force and the right force to balance out. They're pretty close, right? They're a little bit off, but within about 0.2. We'll talk about that a little bit more later. Then our vertical tensions here, those are both positive, those are both going up. We'll talk about that here in just a little bit. Okay? So with that, I'm going to go ahead and fill in the rest of this table, and then we'll be able to answer hopefully the rest of the questions here. All right. So now that we've got our data done, we're ready to start answering some of these questions. The first one that they ask is to verify that the horizontal forces are equal, right? That's what we talked about at the beginning. We believe that the horizontal components of those forces needed to be equal so that the mass would not be accelerating to the right or left. And so we see that. I mean, especially here in the beginning, those are really, really close, especially within the amount of error that we believe that there is. If you looked closely at the spring scales, each mark was about 0.4, which means easily our error could be plus or minus 0.2. And obviously, because they're not perfect, we're going to get slightly more error than that. And so being off by a little bit is fine. You know, if you look at the 8.30 and the 7.53, if I were to average those two numbers, 8.30 plus 7.53, and then divide it by 2, the middle force there would be 7.915. And so you'll notice that this number is about 0.4 bigger than that, and that this number is about 0.4 below that, right? And so we've got this plus or minus about 0.4. Most of our values are within that kind of plus or minus 0.4 range, and so that's not bad at all. But that does give us some idea of the error that must be taking place. And so how much error is there? Well, we're definitely seeing up to about plus or minus that should be a 0.4 newtons, right? It's a little bigger than the 0.1 that we talked about at the beginning, but it's still an acceptable amount. I mean, that's the absolute uncertainty. And if we wanted to find the percent uncertainty, then we would just take that value, that 7.915, and we would take this, and so you would take the absolute uncertainty, and then you would divide by the actual value. And so if we take that 0.4 and we divide by the value of 7.915, and we push enter, then we get 0.05. And so that's about a 5% uncertainty, right? So not bad, right? And that's down here at this end. As you go on, you may see different values. So we've looked at the horizontal forces. We basically said that they more or less balance out, plus or minus a little bit of uncertainty there. Now we're going to look at the vertical forces. So for the vertical forces, we're going to do the sum of the forces equals ma. That's Newton's second law, right? And we did this. We said sum of the forces equals ma. I recognize in class maybe I didn't mention this symbol. If you've never seen this symbol before, sometimes it has kind of little things on the end. But this symbol is the Greek sigma. What that is that's the summation. You add all those things together. So what this equation is really saying is we add up all the forces, and that will be equal to the mass times the acceleration. Now, what we're looking at right now is just the vertical forces. So you could, if you want, say the sum of all the vertical forces will result in a vertical acceleration, the y component, right? And so taking that, we do know that for our mass, our acceleration is 0, right? Because it's hanging there, it's staying hanging there. It's not changing its velocity in any way, shape, or form once it's in equilibrium. So this side of the equation is going to be 0 because A is 0. On this side, I had 3 vertical forces, right? I had the tension 1, the y component, right? Because tension 1 had a vertical component there. And then I had the vertical component of tension 2, which was also up. So that would have been plus T2y. And then I had one more vertical force, right? We haven't really talked about this one yet, but we did have the force of gravity pulling down on the mass. And so I'm going to put that as minus Fg. Now, it is the sum, but adding a negative number because gravity is downward Adding a negative is the same thing as subtracting. And so this ends up working out just fine. So we'll leave it this way. So now we're going to try to put this in terms of variables that we measured, variables that we know, and the one variable that we're looking for, which is the mass. So we've already actually done the first two here, right? We did this on the first page of the lab. That was the first thing that we did. And so this is T1 sine theta 1. This one is T2 sine of theta 2. And then minus the force of gravity. The force of gravity is mg, right? The mass of the object times the gravitational acceleration. That still equals 0. Now you'll notice that the variables that we have, T1, theta 1, T2, theta 2, those are all the things that we measured. So all of this is in terms of things that we measured. The m, that's what we're looking for. That's our unknown, right? So we want that here too. The g, well, we didn't measure that, but we do know it, right? At the surface of Earth, it's 9.8 meters per second squared. So all of those are either things that we know, things that we measured, or things that we're looking for. All right? Now, that's helpful because the next thing that we're going to do is we're going to rearrange this so that it is in y equals mx plus b format. Now, when we do this, you can't just randomly move stuff around. You want to make sure that the y and the x have the things that you measured. Okay, things that you know. You can't have any unknowns in y and x. Those have to be your variables, your independent and dependent variables, the things that you're measuring. Okay, so in this case, you'll notice that those were things that I measured. So those things, that term right there, could be either x or y. This one right here is also things that I measured. That could be x or y. This one has the mass in it. That's my unknown. That means that this term should not be in the x or y position. All right? So I am going to go ahead and rearrange this. I think that the easiest way to do this is just take one of these two and shift it over to the other side. So I'm just going to take the T1 sine of theta 1. There's not really a reason for why I'm doing that one instead of this one. It's just that one's first. So I'm going to take that and subtract it to the other side. Okay? So what we end up getting is this. We get T2 sine of theta 2 minus mg equals negative T1 sine of theta 1. Okay? So now I've got y over here and my mx plus b over here. What I would like to do though is I want this to be positive so that y is positive, and then I'm going to flip this, flip the sides so that I've got my y here and my mx plus b on the other side. Okay, so I'm going to multiply everything by a negative, which is going to make this negative, this positive, that positive, and I'm going to move this to the other side. So I'm going to have T1 sine theta 1 is equal to, so now I'm going to have negative T2 sine of theta 2, and then the negative times the minus mg will be plus mg. All right? Now, you may say, well, that seems like a lot of work. What's the whole point of all that? Well, if we look at it and say, okay, if this is y equals mx plus b. Remember, I was talking about how the thing that you measured needs to be y. So y is going to be T1 sine of theta 1. Okay, that's what I'm going to put on the y-axis of my graph. And then x is going to be this right here, the T2 sine of theta 2. That's going to be x. Now, what you'll notice is if I do that, if I put the things that I measured in for x and y, and sometimes you'll end up with a constant here as well. That's fine. That's not a problem. But the things that you measured need to be inside of that x and y. Okay? They should not be inside of the slope or the y-intercept. Because what you'll see now is that my slope, my m, should be negative 1. And hopefully we'll see that when we graph this in just a little bit. It may be a little bit off, but hopefully it's close to negative 1. What we also see is that my y-intercept should be mg. So if my y-intercept is mg, then if I can find the y-intercept of my graph, and I know G, then I can calculate M. Now the reason for this, because technically I could have just taken this equation and put in all of these values and solved for M. But then I'd have to do it for every single value. And then I'd have to average the values. But is an average really the best way to do it? Well, if you've done averages, means, medians, modes in math class, you may have learned that sometimes an average is not the best way to approach finding that central value. And so doing all that and finding an average isn't always, isn't the most efficient way, isn't the best way to get the best answer possible. So what we're going to do instead is we're going to put all the data on a graph, hopefully create a straight line. If it gives me a straight line, then I will get the best fit line, which that's a much better mathematically, more efficient way of finding the best fit instead of doing an average. And then I can find the y-intercept and the slope at times. The y-intercept will then allow me to find whatever my missing variable is. And then I only do one calculation really, instead of doing multiple ones and trying to figure out how to put those values together. All right, so with that, we've gotten to this point. Let's go ahead and go look at the graph and put that together and see what we end up getting. All right? Now, as we graph it, I'm doing T1 sine of theta 1 on the y-axis, right? And I'm doing T2 sine of theta 2 on the x-axis. All right? Now, I did all these calculations already, right? That's these guys right here. So these are actually the points that I'm doing. Okay? These are going to be my T1 sine of theta 1 is going to be my y values. These are going to be my x values. All right? So again, I'm going to go ahead and pause it for just a minute. I'm going to create a graph that needs to go everywhere. The x values need to go from 1 all the way up to about 4. Okay? And so I'm looking, I think that if I start with 0 here, and then I make this 0.5, and I go 1, 2, 3. Oh, I'm not going to be able to go all the way up to 4. So instead, I'm going to go 0.5 here. That'll be 1. This will be 2. This will be 3. This will be 4, 5. So each one of those dark lines is going to be 0.5. So that's going to be 1, 1.5, 2, 2.5, 3, so on and so forth, all the way down. Okay, on my y-axis, the T1 sine of theta 1, I need to be able to go all the way up to 7. Okay, 7.2 in fact. And so if I count 1, 2, 3, 4, 5, 6, 7, it looks like on this axis, I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, just like that. Okay, I want to be able to use as much of the graph as possible, but I also want to be able to fit all of my points on my graph. And so that's the next step, is we're going to actually put each of the points on here. I will pause it and put the points on because you don't need to see me put the points on, but then I'll come back and we'll try to answer the last couple of questions. All right, so you can see I got my data plotted on here. And so now it wants me to draw a line of best fit and use the graph to determine the unknown mass. So my line of best fit, I'm going to do my best to kind of fit my points. Always you just use a straight edge, a ruler if possible, but something straight. Okay, and we'll go something like this. All right, and that fits the points pretty well. Now you may remember that early on we were talking about our uncertainty here in the angle and in the force, right? The angle we said might have been off by plus or minus 1 degree. And then the force we said could have been off by about 0.1, but then we found out down here that we were off by as much as 0.4 at times. So I'm going to go ahead and use an uncertainty of 0.4, okay? Now, when we show that on the graph, we have to put this idea of T1 and sine of theta 1 together. And so it's the uncertainty of each of those that we have to combine. Now, in our data booklet, it shows us that when we multiply two variables together, that what we do with the uncertainties is that we're supposed to take the percent uncertainty or the fractional uncertainty of each of those, and we're supposed to add those together. And that will tell us what the uncertainty in T1 sine of theta 1 is. All right? So that's actually what we're going to do. We're going to say, okay, so when we look at these data points, and I'll just do one of them. It shouldn't be too different for any of these points. But if I look at the fractional uncertainty of the angle, right? We said it was plus or minus 1 degree. You might say 2 or 3, but 1 degree. So that would be an uncertainty of 1 divided by the actual value or the value that we measured, which was 20. And then I'm going to add the fractional uncertainty in the angle. Now, really, I should be doing something with the trig function here, but we don't actually get into that in this course. So I'm just going to go ahead and use the rule that we know that we'll use for multiplication, which is just the uncertainty of b, which we're going to say that that was 0.4, divided by the value, which is about 10.2. All right? And if we do that, that should then give us the new fractional uncertainty when I put those two things together. All right, so the fractional uncertainty, we're going to go 1 over 20 plus 0.4 over 10.2. And that gives me a fractional uncertainty of 0.089. Okay, now that should be equal to the absolute uncertainty divided by the actual value. Now, for the one that I just did, that was the 10.2. When I did that, the value that I got was 3.49. That's the T1 sine of theta 1. And so this would be divided by 3.49. And so what is x? Well, it would be this number. That's 0.089. And then I'm going to multiply it by 3.49. And I get 0.31. So that is the uncertainty. That's the absolute uncertainty, 0.31, in that measurement. Okay? Now, if I were doing this for real, if I were doing this for an IA, I would want to go through and do that for each of my points. For today, we're just going to assume that because the angles are fairly close to each other, because the measurements are fairly close to each other, it's going to be about plus or minus 0.3 in all directions. So that would be about this far. So each of my data points is going to have those error bars that go plus 0.3 and minus 0.3, just like that. Okay? And you'll notice that my straight line passes through each of those sets of error bars, right? Now that's important because if it passes through those error bars, then we can reasonably say that our data is a straight line. If it does not go through those error bars, then we have to say, well, maybe my data isn't a straight line. Maybe it's some other type of function. And then we would have to look at that and consider what else it might be. But the fact that we can draw a straight line going through all the error bars is a pretty good sign. All right. What we'll notice, remember when we did the calculation before, when we looked at this and we put it into our y equals mx plus b, we found that the slope should be about -1, okay? And so I'm hoping that when I look at my values here, I have a slope of about -1. So this is down 1, and then over 1 here would be from 0.5 to 1.5. So it almost goes over 1. Okay, if I take another point here, so if I go down 1 and then it goes over, so it's not quite a slope of -1. My slope's off just a little bit. That's all right. If I look at my y-intercept here, my y-intercept looks to be about 8.6 maybe right there. So my y-intercept equals 8.6. Now remember, again, in our equation, we said that the y-intercept was mg. And so that should equal m times g. But we know what g is. G is 9.8. And so if I do 8.6 equals the mass times 9.8, and I punch that into my calculator, I would get 8.6 divided by 9.8, and I get a mass of 0.876 kilograms. All right? And so that's the mass that I end up getting from my calculations. And this is using the graph. Okay? We talked about earlier that I could have just plugged a bunch of numbers into the equation and calculated M, but that would not be using the graph. When they ask you to use the graph, they want you to do this. They want you to draw a straight line. They want you to calculate M, right? They want you to get the slope and then connect that to something in your equation. And that pretty much wraps up the lab. So we found a value. It was about 800 something grams, which is all right. I happen to know that the mass that I used was 1 kilogram, but I got 870 grams, so that's within about, 13, 14%. That's not bad. When we're doing these types of physics things with very analog measurements, with the spring scales, with, kind of ignoring friction and other things, but knowing that friction's really there. All those types. When we do labs like that, we expect to be within 20 to 25% error. And that's where we were. We're well within that range. So I think the data is fine. We got some good results. We got a number fairly close to what we expected to get. At this point, what I would like for you to do is finish up the lab by thinking about some of the parts of our experiment that maybe were weaknesses. What are some of the limitations? What are some things that maybe we could have done that would have allowed the experiment to be a little bit better? So go ahead and think through that. Think through whether you zeroed the spring scales. Think about whether we considered all the forces. Think about, how careful you were being when you were measuring the angle, right? Think about all those things. Try to think of a couple of things that you could do. If you were to do this again, how could you do it a little bit better? What could you change that would possibly give you better results and hopefully give us something closer to the real answer? All right? With that, we'll go ahead and wrap it up. Thanks for joining me today. I hope that this video was helpful in completing that lab, and I'll see you next time.